Hello everyone and welcome to the drone building tutorials in my diary dedicated to the development of a drone and an advanced control system from scratch. We will build a drone and a control system using a Teensy or STM32 microcontroller. The idea is to build a low-cost drone that can be used to learn and demonstrate the performance of advanced control and estimation algorithms such as Kalman filters, optimal controllers, adaptive controllers, model predictive controllers, etc. We will not rely upon the well-established flight controllers such as, for example, Pixhawk. In this video tutorial, I performed tests of one of the drone motors and I explain how to control drone motors using a Teensy microcontroller, electronic speed controller, and a pulse width modulation signal. Currently, we are using a Teensy microcontroller. The programming of Teensy microcontrollers is very similar to the programming of Arduino microcontrollers, and in fact, we use the Arduino development environment to program Teensy microcontrollers. Everything explained in this video tutorial can be easily generalized to the STM32 microcontrollers. In fact, I have a complete series of tutorials on how to code STM32 microcontrollers. Before watching this video tutorial, you should keep in mind that this is an ongoing project and some components might be changed in the final design. The purpose of this tutorial and my diary is to document my trials and possible errors, as well as to illustrate to students and engineers a complete development cycle. By watching this video tutorial, you will learn what to do and, more importantly, what not to do. Also, I have to mention that I don't take any responsibility if after watching this video tutorial a person creates a property or equipment damage, or if this person injures himself or herself. Be very careful when operating drone motors and drone batteries, and always be careful and first study the manuals and always strictly stick to the safety protocols when operating drone motors and batteries. In order not to injure myself while testing the motors, instead of using this 10-inch propeller, I am actually using a very funny cardboard propeller. However, this cardboard propeller can also injure your fingers. Let me show you something. Now I will spin the motor with maybe around, let's say, 60 or 70% of duty cycle. Let me show you one thing. Okay, you can see what happened right now, right? Well, this is not even the maximum speed. And you can see how this support is actually oscillating. Now, let me increase the motor velocity to the maximum motor velocity. And just listen and observe the difference. Okay, I don't even dare to take this pen and to touch this cardboard. So keep in mind that this motor can actually spin with the angular velocity of around 10,000 RPM. That's around 170. Also, I have to mention that these tutorials are not for impatient and easy to be distracted people. To become a real engineer, you need to practice to stay focused for a long time period. The complete experimental setup is shown over here. It consists of, number one, brushless DC motor with a motor velocity constant of 920. This means if I provide 1 volt to this motor, the motor will spin with 920 RPMs. Usually we power up this type of motor with nominal voltage of 11.1 volts. This will create around 10,000 RPMs. Here I'm using a low-cost motor named Ready to Sky. In the future tutorials, we will also test other types of motors. Then we have this device over here called electronic speed controller, or briefly ESC. This electronic speed controller is rated for 40 amps. This might be an overkill for this particular motor, since I believe that this motor does not consume more than maybe 10 or 15 amps of current. This is a low-cost motor driver purchased on Amazon. I could not find any documentation about this motor driver, and consequently I had to go over the documentation of similar motor drivers available on the internet. However, in the future I plan to purchase ESC drivers with complete documentation. Then we have a lithium polymer battery with a capacity of 1500 milliamps hour, or mAh. Here we use this battery only for testing. In the final design of our quadcopter drone, we will use this battery that can power up all 4 motors. This is a lithium polymer battery with a capacity of 5200 milliamp hour and with a nominal voltage of 11.11 volts. And I forgot to say that the nominal voltage of this battery is 11.1. This battery consists of 3 cells, and every cell provides around 3.7 volts. If you multiply 3 by 3.7, you will approximately obtain the nominal voltage of this battery. Then we have a Teensy microcontroller, and we have a breadboard and connecting wires. Here we are using pin 3 of the Teensy microcontroller to send the pulse width modulation signals. On the oscilloscope screen, you can observe the pulse width modulation signals generated by the microcontroller and sent to the ESC motor driver. We can change the speed of rotation of the motor by changing the duty cycle, that is, by changing this width of the pulse width modulation signals. For example, to stop the motor, we will change a single parameter in our code. Then, to start the motor, we will again change a single parameter in our code. Let me illustrate that. Here is the code for controlling the motor. I will explain this code later on. To illustrate how to start the motor, I will change this number over here and I will set it to 138. Then I will upload my code, and now you can simply listen what will happen. Then you need to wait a while for the code, and as you can see over here, the motor is spinning. Now let's play with the code and let's try to increase the motor velocity. To increase the motor velocity again, we will change this number. Let's set this number, for example, 200. And as you can hear, the motor is spinning very fast. Now, over here on the oscilloscope, you can actually observe the pulse width. If you compare this pulse width with the pulse width that's from the beginning of this video, you will see that this pulse width is significantly wider. Now, let's go back to our code and let's decrease the speed of the motor. And now you can already hear that the motor spins with a lower angular velocity. And by looking at the oscilloscope screen, you can actually observe that the pulse width is actually smaller compared to the previous case. In the sequel, we will explain the wiring diagram and we will explain all the components. Here is our experimental setup. It consists of Teensy 4.1 microcontroller. In this tutorial series, we will use this microcontroller. The code for controlling the Teensy microcontroller is almost identical to the Arduino code, and consequently everything explained in this tutorial can easily be generalized to Arduino microcontrollers. Then this device over here is called the electronic speed controller, or briefly ESC. This is our motor driver. Currently we are using a 40 amp ESC. This motor driver contains a separate circuit called BEC. If you zoom over here, let me try to do that, you'll see BEC. BEC is a very important circuit. BEC is an abbreviation for a battery elimination circuit. Essentially, the BEC circuit serves as a voltage regulator that steps down the voltage of the lithium polymer battery from 11.1 volt to 5 volts. BEC enables us to power a microcontroller or some other device, such as a servo motor, by using the main lithium polymer battery. In this way, we don't need to have a separate battery for our microcontroller or some other electronic or electromechanical devices on our quadrotor or drone. To use the BEC voltage, we need to use the red and the black wire over here. The red wire provides constant 5 volts and the black wire is actually the ground. We will talk about the white wire over here later on. This is a pulse width modulation signal wire. That is, through this wire we send pulse width modulation signal. To reduce the costs, we are using a low-cost 40 amp ESC available on Amazon. Unfortunately, this battery does not have specifications available online. However, everything explained in this tutorial can be generalized to other types of ESCs. Then, we have our motor. This is a motor with the motor velocity constant of 920. In this tutorial, we use a low-cost, ready-to-sky motor. The motor velocity constant is denoted by kV. In our particular case, 920 kV means that if we provide 1 volt to the motor will spin with the angular velocity of 920 rpm. On the other hand, the nominal battery voltage of 11.1 volt will spin the motor with the angular velocity of approximately 10,200 rpms. This is approximately 170 revolutions per second, and this is a very high angular velocity for such a small. Then we have a lithium polymer battery with a capacity of 1500 milliamp hours, or briefly mAh. The lithium polymer battery is abbreviated as LiPo. Our battery has a nominal voltage rating of 11.1 volts. It has 3 cells. Every cell provides 3.7 volts. If we multiply 3 by 3.7, we will actually obtain our nominal voltage of 11.1 volts. Then we have a breadboard with connecting wires. The connecting diagram is very simple. Our ESC has 3 ports. First port, second port, and the third port. The first port is actually the connection to our lithium polymer battery. This connector over here is called XT60 connector. Then, the second port has 3 connectors, or 3 wires, and here it is. We have a white wire, we have the red wire, and we have the black wire. The white wire is actually our pulse width modulation wire, or the wire that will carry the pulse width modulation signal. Then we have a red wire of 5 volts. This is actually the power provided by BEC circuit. And we have the ground, that is the black wire of our BEC circuit. And finally, we have the third port consisting of 3 wires that are connected to our motors. You can simply take these 3 wires and you can plug the motor wires, and the motor also has 3 wires, and you will establish the power connections. Again, ESC, we have the connection to our lithium polymer battery, then we have these 3 wires. The first one is PWM, and the second and the third wires inside of these 3 wires are actually BEC, power and ground, and then we have these 3 wires on this board connecting actually our ESC to the motor. Let's analyze what's happening over here. Here's our Teensy 4.1 microcontroller. We will only be using 2 pins of this microcontroller. We will be using the pin number 3, and this pin will be set as the output pulse width modulation pin, and we're using this ground pin over here. This ground pin is connected to the common ground of our breadboard. At the same time, the ground of our BEC, that is the black wire over here, is also connected to the ground of our breadboard. That is, the ground of microcontroller is connected to the ground of our BEC, or better to say also the ground of our ESC. Okay, then this pin, you can track it over here, is attached over here. And through the breadboard, this pin and through this white wire is actually connected to the pulse width modulation wire of our ESC. And that's it. That is, the pin 3 is connected to the white wire of our ESC, providing the pulse width modulation signal. So what happens in practice? We will write a code and we will send pulse width modulation signals to pin 3, and from pin 3 these pulse width modulation signals will be sent to our ESC. Next, let's explain how to control the motor. Unfortunately, for the particular ESC we are using, we were not able to find the exact specifications. However, our ESC is not significantly different from similar ESCs available online. Consequently, we search for specifications of similar ESCs available online. And we obtain the following information that is also confirmed by our experiments. As mentioned previously, the DC drone motors are controlled by using the pulse width modulation or PWM signals. And here's one example recorded by our oscilloscope of a pulse width modulation signal. The PWM signals are quantified by the period or frequency of the PWM signal and the width of the pulse of our pulse width modulation signal. The period, denoted by capital T, is given over here. On the other hand, the pulse width, denoted by capital W, is shown over here. According to the information found in manuals of ESC motor drivers, the pulse width for controlling the motor should be in the interval from 1 millisecond to 2 milliseconds. Here, 1 millisecond should produce the lowest possible motor angular velocity, and 2 milliseconds should produce the highest possible motor angular velocity. Of course, this highest possible angular velocity is actually limited by our ESC driver. Any pulse between 1 and 2 milliseconds will produce the motor angular velocity between the minimum and the maximum value. The duty cycle D is defined by this ratio. That is, the duty cycle is the ratio of the pulse width and the period of the pulse width modulation signal. We discovered that in practice the start and the end values of the interval do not exactly correspond to 1 and 2 milliseconds. There are small deviations from these values. On the other hand, we also have the freedom to select the frequency of the pulse width modulation signal. That is, we have the complete freedom, or not exactly complete freedom, to select this period T. In our experiments, we use a frequency of 500 Hz. This is mainly because this frequency corresponds to the period of the pulse width modulation signal of 0.002 seconds or 2 milliseconds. That is, the motor will be started at approximately 50% of the duty cycle, and the maximal angular velocity will be reached at approximately 100% of the duty cycle. It is also possible to select the lower frequency of the pulse width modulation signal. For example, we can select this frequency to be in the range of 50 to 500 Hz. However, for the values of the PWM frequency lower than 500 Hz, we might have a saturation limit. This is mainly because the motor will not spin faster for pulse widths larger than 2 milliseconds. We might send a pulse that is larger than 2 milliseconds, however, this might not increase the motor angular velocity. In fact, we discovered that pulse widths larger than 2.5 or 2.6 will actually stop the motor. Consequently, it might be a good idea to use the frequency of 500 Hz or to use a lower frequency. However, in that case, we need to limit the pulse width to 2 milliseconds. The Teensy code for controlling the motor is very simple, and here it is. In our setup function, we will use this function called analog write frequency to specify two things. First of all, here we are saying that to the pin number 3, we will send pulse width modulation signals. That is, the pin number 3 is the output pin. And the second input argument of this function, that is this 500 over here, specifies the frequency of our pulse width modulation signal. Then, over here, we specify the resolution of our pulse width modulation signals. What is the resolution of a pulse width modulation signal? The resolution of 8 bits means that the pulse widths will be mapped into integer numbers that are in the interval from 0 to 255. 255 is actually equal to 2 to the power 8, then everything minus 1. Here, 0 corresponds to the pulse of the 0 width, and 255 corresponds to the pulse of the width of 255, multiplying 1 over, then everything in parentheses, 256, multiplying 500. Now, this is approximately 1 over 500, that is, this is approximately 2 milliseconds. To repeat, 0 is 0 pulse width. And let's go back to our diagram. So 0 is pulse width modulation signal with a pulse W of 0, right? So it's just 0. On the other hand, 255 corresponds to the pulse of the width of 2 milliseconds. That is, this will approximately correspond to the duty cycle of 99.99, almost full duty cycle. Any value between 0 and 255 is our control signal. Let this control signal be denoted by C. Then the pulse width can be calculated by this formula. It's C multiplying 1 over 256 multiplying 500. In our case, that is in the case of our motor and our driver, we experimentally discovered that the motor starts at the control value of C equals 136. This corresponds to the pulse width of 1.0625 milliseconds, and this slightly deviates from the theoretical prediction of 1 millisecond. Actually, this is in a very good agreement with information found in manuals. In our infinite void loop, that is over here, we use this function called analog write to actually send the pulse width modulation signal. The first input argument is the number of the pin, in our case pin number 3, and the second input argument is actually the value of the control signal. So here is 150, and to calculate the actual pulse width, we need to use this formula. We will plug in 150 over here, divide the result by 256, and divide the result by 500, and we will actually obtain the pulse width. That is how we control the motor. Now, depending on the ESC driver, the starting pulse width and the end pulse width defining the control range might not be exact. For example, it might happen that the motor starts at 1.1 milliseconds and that it stops at 1.9 milliseconds pulse width. Consequently, these numbers need to be calibrated. I will explain the calibration procedure in my next video tutorial. For the time being, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.